Hello everyone, good afternoon. Thank you all for being here. So we are going to talk about algebraic data types and pattern matching in Java and how these features help us write readable, understandable Java code. Okay, so let's get started. The process that we're going to follow in this talk is that we start with a problem. This problem is actually going to be a puzzle. So we will solve the puzzle during this talk. And for the problem, we design a solution, and then we will implement it using algebraic data types and pattern matching. And then we will have easy to read, easy to understand code, hopefully. I think so, but we'll find out. Okay, my name is Balkrishna Rawool. I work as IT chapter lead in ING Bank, and I've been using Java for many years. But it's the recent features that really excite me. We're going to use some of them, more specifically records, seal types, and pattern matching. Okay, so let's get started. I said the problem, right? And the problem that we're going to solve is this. Now, what we see here is a mathematical equation, and the numbers are replaced by letters. And the idea is to find out what are the numbers behind these letters. Now, has anyone here seen this or similar problem before? Okay, some. Now, out of these people, have you able to solve this? Have you been successful in solving this problem? Well, I see some hands raising slightly. Yes, a few hands. It's really good. And have you solved it without using a computer? Wow. Okay, so we really have some puzzle lovers in the audience. That's really good. Good to have them. Well, actually, I chose this problem because it's easy to understand, but it's difficult to solve, right? And those who have solved it probably understand. Yeah, let's try to analyze this problem. What are we dealing with? What are the rules, right? So this is the problem, and these problems are known as crypt arithmetic puzzles. There each letter corresponds to a single-digit non-negative number, right? All letters have unique numbers, and letters placed together form multi-digit number. Like for example, send, more, or money. All of these are 4 or 5-digit numbers. And one of the rules is that the letter M here in this specific example cannot be 0. But let's take a moment and look at let's say the first the significant bits or significant digits or significant letters from these two numbers, send and more, S and M, right? They add up to MO. Even if you assume the highest numbers at S and M, 9 and 8, and if you add one carry, it will add up to 18. It can't be 20 or more. Therefore, M cannot be 2 or more, right? It has to be 0 or 1. Right? That's a simple logic of deduction. And then we can deduce that if it cannot be 0, it has to be 1. So actually, we have solved it for one letter. If we continue doing that, and then we can also solve the entire equation. But it gets difficult, and we will find out why. And the last rule is the equality constraint must hold true. So send plus more has to be equal to money. Okay, so let's try to analyze this a bit. What we see is that here we have 8 letters: S, E, N, D, M, O, R, and Y. And there are a bunch of rules, right? What we saw earlier. So each letter has 10 possibilities, 0 to 9, except M, right? M has 9 possibilities. Each letter has a unique value. Then M cannot be 0. That means it has to be 1, like we saw earlier. And send plus more has to be equal to money. Now, if we start with all the possible values that these letters can have, we start with about 90 million combinations. And then we reduce it down to 181,000 combinations by applying these constraints one by one. But still, this is a really high number to do it manually. And when we apply the final constraint, we will have our solution or solutions. We don't know them right now, but we will find that out. Now, this technique of starting with the problem and applying different constraints to come up with a solution is called constraint programming. In constraint programming, you have a bunch of variables and a bunch of constraints that are applied to those variables, right? And there are two kinds of constraint problems. So you have constraint satisfaction problem and constraint optimization problems. The one that we are dealing with is constraint satisfaction problem because we only have to satisfy certain constraints. In constraint optimization problem, you also have a thing called as object function. right? And so along with satisfying all the constraints, you have to have a maximum or minimum value for that object function. But again, we don't have to worry about optimization problems. We are only looking at satisfaction problem. And there are a bunch of Java libraries that do this, like ChocoSolver, JSolver, OptaPlanner, and MiniCP. But we are not going to use any of these libraries. What we are going to use is our understanding of constraint programming and how we will use that to solve this puzzle. Okay, let's talk about some goals and non-goals. We don't aim to write the most concise implementation. Right? This is not a code goal. We are not going to reduce it down to the less number of characters or anything. That is not the idea here. And also, we don't want to write fastest running program. But we do have to have a program which finishes in a reasonable amount of time. We don't have much time, right? So what we do aim here is to solve the problem at hand. We definitely have to solve it. And to keep it verbose enough so that it is clear and readable, right? So let's not get rid of verbosity completely. Let's keep it verbose enough so that it is readable. And it has to be extensible. So let's say we have other cryptarithmetic puzzles where we have different kinds of constraints. It should be possible for us to add those constraints to our program and then solve those puzzles as well. And also, our aim is to learn about algebraic data types and pattern matching. Well, a lot of goals. So let's get started. Solution design. So for this problem, we can have a, let's say, straightforward solution to come up with all possible combinations of values for these letters, and then apply this equation. And wherever that, let's say, all the constraints are satisfied, we would have a solution, right? That would be a straightforward approach, and that we can divide into three components, starting with a component called generator, which generates all possible combinations of values. And then we have expression evaluator, which evaluates different expressions. And then we finally have a puzzle solver, which basically uses the generator and expression evaluator to generate all combinations and evaluate the expressions. And we check that all constraints are satisfied, and then we have a solution. Okay, so it looks like this. You have a puzzle solver, which uses generator, which generates all different combinations, and then it uses expression evaluator to check if all constraints are satisfied or not, and if all of them are satisfied, then we have our solution. Okay, now let's zoom in on the expression evaluator part, right? And let's look at a very specific expression or an example of an expression, send in this case. Now, send has 4 letters, S, E, N, and D. And if their values are small letter S, E, and D, then we get the value of this expression send as S times 1000 plus E times 100 plus N times 10 plus D, right? And if we represent this expression using a binary tree, it would look something like this. Now here, if you traverse this binary tree using in-order traversal, you would get your expression, right? You will get the value of your expression. Now, let's do that. So starting with the bottom left corner, it would be S times 1000 plus E times 100 plus N times 10 plus D, right? And there's something really interesting about this tree, is that if you take any node and create a subtree, treating that node as a root node, you will still get valid expression. For example, if you use the leftmost plus, then you get a subtree which is S times 1000 plus E times 100, which is still a valid expression. If you use D as your root node, you would get expression D, which is still a valid expression. And if you use the multiplication sign between n and 10, you get n times 10, which is still a valid expression. Or if you use just 10, that is still a valid expression. So there are a bunch of valid expressions, and if you look at all of these possibilities, all of these combinations of expressions, you get a grammar for your expression, and it looks like this. So an expression can be a constant, or a variable, or addition of 2 different expressions, or multiplication of 2 different expressions, right? So this grammar would represent all possible valid combinations, and it would completely eliminate invalid expressions, right? Now, this kind of grammar can be best implemented or best represented using what is known as sum type. And sum type is a kind of algebraic data type. So let's look at algebraic data types now. Okay, algebraic data types, what are they? They are the types created by combining existing data types, mainly by applying algebraic operations. And there are 2 main categories, sum types and product types. Let's look at both of them in a bit more detail. Starting with product types. Now, in product types, each possible value of new type is actually, let's say, has a value for each of its constituent types, right? So an example of this could be a point has two coordinates, x and y. Now in this case, each instance of point has a value for x and a value for y. And how would you implement that in Java? You would use a record. So record point in this case has two constituent types, both of them are int. Another example could be an address has a house number, a street, a city, and a country. And then in Java, it would be an address record with one integer and three strings, mainly representing house number, street name, city, and country. Now, why is it called product type? For that, let's consider three different sets. Now, here you have set A, set B, and set C. Each of them have two elements. And these sets also represent types. So there are three types, A, B, C, and the elements of these sets are actually instances of these types, right? So if you imagine this scenario, then your product type of these types will be ABC, which has value for each of its constituents. So it would be these elements, right? Now, if you look closely, you will see that this resulting type is actually a Cartesian product of your sets, right? So in set theory, the equivalent of product type is Cartesian product of your sets, and that's why this type is called product type. Okay, moving on, we have sum types. In sum types, each possible value of new type is one of the values of its constituent types, right? So an example of this could be a shape can either be a triangle, a quadrilateral, or a circle. And in Java, you would implement this using a ceil type, or in this case, a ceil interface. So your ceil interface shape has three implementations: triangle, quadrilateral, and circle, and it cannot be anything else, right? Okay, why is it called sum type? Again, the same equivalency. So we can look at three different types. Each has two elements. And if you create a sum type using these types or using these sets, you will get this. So a resulting type which has value, which is one of the values of these types, right? So this is basically a union of your sets. To be precise, it is a disjoint union. So it's basically the set theory equivalent of sum type is disjoint union of sets, and that's why it is called a sum type. Okay, moving on, we have looked at algebraic data types, so mainly sum types and product types. Let's look at pattern matching now. So pattern matching is basically checking for a presence of pattern in a given sequence of tokens, right? And we have a bunch of features in Java for pattern matching, and few of them are here, which are available in Java 21. So pattern matching for instance of, pattern matching, record patterns, pattern matching for switch, and unnamed patterns and variables, which is in preview, but rest of them are out of preview, they are finalized. We'll now quickly look at examples for each of these, but probably you have seen a lot of examples for records and pattern matching already, but let's quickly look at some examples for these features, starting with pattern matching for instance of. So in this example, you see an expression of instance of, which not only checks the fact that object has a type point, but also creates a variable p, which is of type point, and then you can use that variable in the subsequent code. Record patterns. So if point is a record, then you can also deconstruct that record into its constituent types, and you can use those in your code. And if your point is made up of another record, or let's say if you have records which is using record, you can still use nested deconstruction of your record types. Pattern matching for switch. So we looked at a shape type, right, which could be triangle, quadrilateral, or circle. If that is your ceil hierarchy, then you can have an exhaustive switch expression. In this case, you have a switch which is basically calculating the number of sides of your shape. So for triangle, it is 3, for quadrilateral, it is 4, for circle, it is 0. And again, it's an exhaustive switch, right? So we don't need a default branch in this case. Unnamed patterns and variables. So you can replace unused variables with underscores. In fact, you can use local variable type inference. And in this case, you could also replace the whole, let's say, record type or the record variable with underscore. We'll see that in code when we actually solve the puzzle and create this implementation. Okay, so we have seen algebraic data types. We have seen pattern matching. Now let's get back to solving our problem. The solution steps. So this is our problem, and this is the solution that we came up with, right, with these three different components. So let's start with the first rule, that each rel corresponds to a single digit non-negative number, and we're going to create a variable type to represent each letter, and we are going to create a range constraint type to represent the constraint that you have on the variable, so the range of values that it can have. Then we are going to create expression type, which basically implements the expression evaluator with an evaluation function. I was actually thinking to go through these steps one by one and then do its implementation, but that would be too much back and forth between IntelliJ and PowerPoint. So we'll just go through these steps one by one, and then we'll do the implementation in one go. So after expression evaluator, we implement the generator, which generates all possible combinations of values. And then we need still more constraints because we have only taken into account the range constraint part. We still need to make sure that all the values are unique. So we have unique values constraint, and we need to make sure that the equation is satisfied, right? So we need equality constraint, and that we will create. In the end, we create the puzzle solver by creating a type called puzzle, which basically uses generator and expression evaluator to find the solutions. Okay, so let's get started with the implementation. I'm going to move to IntelliJ. And this is the biggest part of the talk. Okay, you are able to see. Okay, not able to see that. Okay, do I have to switch from this screen? All right. Okay, this would be a bit difficult because I probably have to move this monitor. Okay. Okay, so what we said was that we will have first the type called variable created, right? So let's do that. Let's create a type variable, and it's going to be a record, and this record is going to have name because variable has name, and we are going to create a type called as range constraint, right? So we'll create record range constraint, and okay, let me check if I'm not making any typos in here. Constraint. Okay, and range constraint is going to have two values, int from and int to. Okay, this would be a bit awkward, so I'm going to duplicate the monitors. Right. Okay, so we have both the types created, and the range constraint is basically used in variable range constraint, which will be of type range. Okay, and then the next thing, as we saw. Okay, anyways, the next thing that we saw we will be creating is the expression evaluator. So we'll create a type called as expression, and this will be an interface, and specifically sealed interface. And it's because we saw the grammar for expression as either constant, variable, addition, or multiplication. So for all those four types, we're going to have records which will implement this interface. So we have a record const expression, and constant expression only has a single value, which is just an integer, and this implements expression, and then we have a variable expression, and a variable expression has a string name, and then we have addition expression, which has two expressions, right? So we're going to have an expression left and an expression right, and similarly we will have multiplication expression, which will also have left and right sides. Okay, so we have our data model created, but we also want to add evaluation functionality to this, right? So let me do that by adding a static method which returns an integer, and we call it evaluate. So evaluate takes an expression, and in order to evaluate an expression, you need values of your variables. So we're going to create a map which as string to integer mapping, and we call it values. Right. So how do you implement this evaluation function? We return a switch and switch over our expression. And here IntelliJ really helps you because it adds this code for missing branches. So you can see all your branches created. But here one thing, that the order of these branches is different than the order in which they are defined. So I'm going to just correct that order, starting first with the constant expression. And I'm going to move this addition expression below and the variable expression a bit up. So now we have in the right order. So let's start with the constant expression. Oh, and I forgot to ask you, is the font big enough? I mean, it's a bit too late. Oh, okay. Oh, should I have asked it a bit earlier? Yeah, because like here you have really big screens, so I assume that it is big enough. Let me increase. Font, sorry. And this is it big enough? That was too big. Let me also change the console font while we are at it. Yeah? Perfect. Okay. So constant expression has a value, and if you evaluate constant expression, you will just get that value. If it's a variable expression, then you will have name of the variable, and how do you get the value of that expression? You just look it up in the values, right? So you values.get name. Addition expression. Now this has two expressions on the left side and on the right side. And how do you get a value of the addition expression? You evaluate the left hand side with the values and then add it to the evaluation on the right hand side, right? And the same is the case for multiplication. So basically here you will again have variable left, variable right, and the evaluation is going to be left multiplied by right. Okay, now let's take a moment to understand what we have done here. So basically we separated the data model from the behavior or function that operates on that data model. And by using that, we are able to, let's say, focus only on the data model while writing the data model and focus only on behavior during writing the function. Now, what we would normally do when you see hierarchy like the expression, you would create 4 different classes, right, which are implementing the expression interface or extending the abstract class. And then this evaluation function would be spread across all those classes, which would be fine to do. There is nothing wrong in doing that. But doing this has an advantage. Here, while you are implementing data model, you are focused only on the data model part. And while implementing the behavior, you are focused only on the implementation or the behavior of your data model, right? Also, by using sealed hierarchy, you have some more advantages. So for example, if you miss a branch, compiler really points at you and say, hey, you have to add that branch here. Also, if you say add a new constraint or new expression, so let's say now you have support for division as well, right? And then in that case, the compiler says, hey, you are missing a branch here, and IntelliJ helps us to add that branch. Okay, so basically, a compiler really helps you along the way. And because we are using pattern matching, there are also extra benefits. So you can create a specific branch to handle a specific scenario. So in this case, let's say your division has dividend, and you want to deal with a situation where you have a divisor which is a constant expression, right? And then you have a value which is divisor, and you want to say that when the divisor is 0, I want to throw some exception. Right, so that's also possible. So you could implement those specific scenarios, and this is really the power of pattern matching. So you can create your branches to your specific situation and handle that. Okay, so we have actually seen it enough. Let me just get back to the implementation that I originally had and want. So okay, this is what we want for expression. Then the next thing, if you remember the solution steps, is to create generator. But okay, generator is not the focus of this talk. And to save time, I've already implemented the generator here. But let's quickly take a look at what it does. Now, it is a record which takes variables as its input and also takes an indication whether you want unique values or not. And it creates all these possible combinations, right? It exposes a method called as for each combination to which you can pass a consumer. So every time it generates a new combination, it passes that to the consumer. So you can write your own implementation. You can write your own consumer, which is using those values. And in this case, it is using depth first search, but you could have your own implementation. Also, this is also pretty interesting source code. So if you want to take a look, I will share the link later on. Then the next thing we are going to create. We have created now the generator and the expression evaluator. We have to create the puzzle solver, right? For that, we create a type called as puzzle. But puzzles still take two constraints. We still have to deal with a couple of more constraints. So let's create first an interface which represents the constraints that are going to be set on puzzle. Let's call it puzzle constraint. And again, this is going to be sealed interface. I want to make it sealed because there are only two constraints that are applied on puzzle, and it's good to have them sealed because that will be handy later on. It's basically enforcing the rule that there are only two constraints. So we have first record called as unique values constraint, and that implements the puzzle constraint. And then we have equality constraint, right? So we want the equation to be also checked. Now, equality constraint has two expressions, left and right expression. And so what we can also do is if you have a specific type in your sealed hierarchy, you can add some specific implementation if you want. So in this case, what we want to do is for equality constraint to check that if the equality constraint holds true or not. So we can add a function called as Boolean holds true for, and it takes a map of string to integer, again called as values. And how do we check that if the equality constraint holds true or not? We just return an expression. So we do an evaluation of the left-hand side. Let me import this statically, so it reads nice. So evaluate the left-hand side with values, and then check if it's same as the evaluation on the right-hand side with these values. So when left and right both evaluate to the same value, you have your equality constraint satisfied. Okay, so we have now looked at the puzzle constraint. The next bit is to implement the puzzle solver itself, and we'll create a type called as puzzle, which is also going to be a record. And if you remember the constraint programming slide, so every constraint or cryptarithmetic puzzle has variables and constraints. So we're going to create a list of variables. We call it variables, and we are going to have a list of constraints. So in this case, puzzle constraints. Let's call it constraints. So this defines our puzzle, and when you have a puzzle, what do you do with it? You solve it. Right, so we will have this method called as solve. Now we'll keep the implementation for a bit, but let's zoom out a little bit. So we have now our puzzle constraint. I think there's a typo with the puzzle, and of course the name has to be changed. I could have used the handy IntelliJ shortcut, but anyways. Okay, so we have our puzzle, we have generator, we have expression evaluator. Now we need to solve our specific problem, the problem that we started with, right? So let's create a specific instance of puzzle for our problem, and then we will use this to solve it. So for that, let's create a main class. I could have used unnamed classes, but I chose to use our plain old public static void main. And we are going to need all the variables. So I'm going to generate a bunch of let's say variables now. So these are the variables that we would need: SEND, and if you notice, all of them have constraint from 0 to 9 except M. M has constraint from 1 to 9. That's one of the rules that we had in our puzzle, right? Okay, so let's create a new puzzle, and the new puzzle takes a list of variables. So let's create a list of variables which is SEND, MOR, and Y. And then we are going to also need a list of constraints that we are going to pass it. So let's create a list of constraints. The first constraint is unique values constraint because you want all values to be unique. So you create unique values constraint. And then the second constraint that we need is that the equation has to be true, right? So we create a new equality constraint. And somehow we need to represent our equation, which is send plus more equals money. We will come back and do this. But once you have your puzzle, the next thing that you would do is solve it, right? So let's keep this implementation for now, and let's go back to implement the solve method in the puzzle type. Okay, so what we said earlier was that in puzzle uses the generator type, generate all possible combinations, and then uses expression to evaluate these expressions, right? So let's create the generator. This will be new generator, and what does generator require? Variables and an indication whether you have unique values or not. So let's pass the variables, and we need whether you want unique values or not. And where do we get it from? From the constraints, right? So we need to check if there is a unique values constraint in our constraints. Let's do that now. Unique values needed, and this will be basically constraints dot stream dot any match, and we're going to check the presence of a specific type of constraint. So constraint instance of unique values constraint. So once we have that, then we know that we need unique values. So we will pass that to the generator. Okay, so once we have the generator, the next thing is to basically use the for each combination method, and this is going to give us let's say ability to pass the consumer which gets all the values. So let's do that. Once we have all the values, what you want to do is, if it is a solution, we want the solution to be printed. So let's do that. So if it is a solution, we are simply going to print it. We could do something else, but we just choose to print it. Now, how do you know if it's a solution? Let's create that method. We know it's a solution when all constraints are satisfied, right? So what we're going to do is we're just going to simply return that constraints dot stream dot all match, and for a constraint, we know that it is satisfied. So let's create a method called it's satisfied, and we pass the constraint and values to it. And once all these constraints are satisfied, then we know that we have a solution. And how would the is satisfied method look like? This is basically going to say, let's check if the constraint is an instance of equality constraint. And once it is an equality constraint, let's check if the equality constraint holds true for the given values. Now, the constraint can also not be an equality constraint, right? How do you deal with that situation? Let's add a not here. So when it is not equality constraint, then we are okay. We don't check for the equality, but when it is, then we do. So we add a shorthand or here. So basically what's going to happen is that if it's not equality constraint, we are okay, we return true. If it is an equality constraint, then we're going to check if it holds true, right? And our compiler is doing something smart here. We are using the pattern matching for instance of here, right? So we created this equality constraint, and we are able to use it on the right hand side only because we have a shorthand or here and a negation here, right? If you remove or if you make this normal or, you're not compiler complaints because you can't you're not able to use the equality constraint on the right hand side. Also, if you remove the negation, you're not able to use it because then in that case constraint is definitely not equality constraint, right? So you can't use it on the right hand side. So compiler is actually checking that you are able to this equality constraint on the right hand side, right? And I think it is pretty smart from the compiler, and it deserves a little bit more appreciation than it is getting now. Okay, so we still have to implement our equation here. So what's happening here? This is the left side, and this is the right hand side, and each of these expressions are nothing but a number that is created by using these letters. Now, in order to write that easily, I'm going to create a bunch of methods in this expression, in the expression type, static methods to generate or to create the instances of these types easily. Right, so these are static methods. We just give new instances when you pass these values, and this is going to help us to write code here a bit more nicely. Right. So what we're going to do is we are going to use one of these methods called as add, and we're going to add send and more, and then we are going to check if it is equal to money or not. Let me import this statically. Okay, so each of these numbers, as I said earlier, these are nothing but, let's say, 4-digit or 5-digit numbers created out of these variables. So let me create a method called as create number and then pass these variables. So in this case, it is SEND, and then in this case, it is MORE, and in this case, it is MONE and Y. Okay, now how does the create number method look like? Is basically it is either taking 4 or 5 variables, and it is giving you an expression which is just a number. So then we're just going to use the fact that these are all single-digit numbers, and you can create an entire number starting with the left-hand side and then multiplying it by 10 and adding the next one, and again multiplying the whole expression by 10 and then adding to the next one. So then it doesn't matter if you have 4, 5, or any number of let's say letters in your number. So let me add that method here. So this is what it looks like. You start with the 0, and then for every variable you multiply it by 10 and add it to the next variable in your expression. So let me import these methods. Okay, so looks like we have our complete solution. Now let me run this and see if it actually works. Well, it takes some time, and you have some solution. Now let's check if it is actually a solution. I mean, you might have some numbers which may not satisfy the constraint, right? So let's check quickly. Yeah, I had thought about doing it as a unit test, but then that would have probably given us the solution already. So that's why I chose to do it this way. Now send is 9567 plus more is 1085, and money is 10652. And let me check if the equality is true or not. Oh, sorry, I think I messed up something here. 567, I think, yeah. Yeah, so let me check. Yeah, so I think the equality constraint is it's satisfied here. So basically, we have a solution for our puzzle. And one of the things that we did use is we made use of, let's say, the different features that are available in Java 21, like records and patterns. And we said that we are going to create readable code. I mean, it looks readable, except for one thing, which is really bothering me, and that is this part. I mean, we used it to show the smartness of our compiler, but that's not the aim here, right? Our aim is to write readable code. This doesn't look very readable to me. Right, there is a negation, there is a shorthand OR, so we really have to think what is going on here. Now, can we do something about it? And can we use the fact that puzzle constraint is a sealed interface? Well, actually, we can. So replace this with a switch, which is again going to be an exhaustive switch. So constraint, and then again, IntelliJ helps us to add these branches. Okay, let me put it in the right order. So first, unique values constraint. So if it is a unique values constraint, we have already taken care of it, right? So at this point, it is already satisfied. So we can simply return true. And if it is also we are not using this variable here, so we could simply replace it with underscore. That is only possible if you are using Java 21 in preview. So if you are not using preview, just like any other Java developer, you can just do double underscores. But okay, let's not do that. If it's an equality constraint, then we just check for equality constraint holds true for the values. And now it reads much nicely, right? So you have different types. Again, it's exhaustive, so compiler is really helping you. And let's again run this and check if it is actually giving us the same values or not. Otherwise, it would be a shame. But now it does. So I think, yeah, we have our solution, and the code looks readable. We have also used the fact that our data and functions or behavior is nicely separated, and we have used these different features to make it read really nicely. Okay, so now let's get back to our presentation. Let me see if I can do that very easily. Yeah, okay. So yeah, we did go through all of the solution steps to implement our solution, and we used the algebraic data types and pattern matching to implement the this constraint, this hierarchy of expression. So what did we do? We kept the data and behavior separate. We used algebraic data types, which helped us to model the data so that only valid states are allowed to exist. We use records and seal types to implement product and sum types. And we use pattern matching features to implement the behavior, right? The functions that operate on that data. Now, this style of programming is called as data-oriented programming. And I assume this is not the first time you're hearing it in this conference, but let's again revisit it because it is quite an important thing to look at. So data-oriented programming encourages us to model data as immutable data and keep the code or the behavior that operates on that data separate, right? And it is explained really nicely by Brian Gates, the Java language architect at Oracle, in this article. So if you go to that URL, you will get to an InfoQ article where it is really extensively explained with different examples. And there are 4 core principles that he mentions there. The first one is model the data, the whole data, and nothing but the data, because data is at the center of it, at the core of the data-oriented programming, right? We should ensure that we don't have, that we only allow valid data to exist, right? And data is immutable. You can use records to create shallow immutable types, but you can also use other immutable data structures to make your program or to increase the immutability of your application, right? And that really helps you get rid of a lot of problems. Validate at the boundary. So data-oriented programming is very useful for small subsystems, right? So, and if you have a subsystem which has a boundary with, let's say, another external system, right? For example, let's say you are getting a number from another external system, and the number is coming in a string or text format. You have to basically transform it into your own type. So what you would do is at the boundary, you would validate that this string is actually a number, then convert it into your integer or double or float, depending on what is the data model that you want. And within that subsystem, then you are able to use that type, transform it to whatever type that you want, right? So you don't have to validate it again within the subsystem. And then make illegal states unrepresentable. So like we did with expression, we use algebraic data types and pattern matching to make sure that the illegal states are not representable in the subsystem. Okay, so you use ADT and pattern matching. So in other words, record, seal types, and pattern matching to enable easier data-oriented programming. And the last thing, the difference between OOP and DOP. So object-oriented programming is useful for modeling large, complex systems, and data-oriented programming is suitable or is useful for simpler, smaller subsystems. Yeah, that is all I had. If you want to take a look at the source code, so it's available on GitHub on this link. If you have any suggestions to improve it, because the idea is to make readable, understandable code. So if you have suggestions that can improve this code, do let me know, or just send a pull request. That's also fine. And there's interesting stuff happening at ING. So if you're interested in that, you can reach out to me or my colleagues who are sitting in the audience or downstairs in the booth. And yeah, so if you have any comments, questions, mistakes to point out, you can reach out to me here. And please don't forget to rate the talk. And thanks for coming. Thank you.